Lesson 9.1 is polar coordinates. The polar coordinate system is a naming system for points in the plane, similar to the Cartesian system is a system for rectangular coordinates or the XY coordinates that we've been using. So it's just another way to plot out points. So the parts of a polar coordinate system is we have the pole, which is like our origin in our XY plane. You have the polar axis, which is in the same direction as what would be our positive x-axis. And then we have an angle, which we call our polar angle. Usually we use the Greek letter theta to represent. And then we have a distance away from the pole, which we use r like a radius. So instead of a coordinate point xy, which measures how far left or right you are and then how far up or down you are, our coordinate is r comma theta, which is the angle that you're making with the polar axis or the positive x-axis and the distance out from the pole. Just like in trig or in geometry like we were talking about, positive angles go counterclockwise, so they go up from the positive x-axis like this. So this point here, 2 comma pi over 4, would make an angle of pi over 4 with the positive polar axis and then go out a distance of 2. If you were to have a negative radius, it would actually flip and go backwards. So if you had a angle theta, but then a negative radius, it would reflect across the pole and come down that distance. So for example, the point negative 3, 2 pi over 3, you'd go an angle of 2 pi over 3, and then you'd go negative 3, but in the opposite direction, so it would end up down here. So we want to graph in the r theta plane. So this is what we usually make look like the r theta plane, kind of like a unit circle-ish looking thing. And then coordinates are always alphabetical, just like xy, it's r and then theta. But we actually go the opposite direction when we graph it. We always graph the angle first and then the radius. So if I want to graph this point P, which is 2 pi over 3, I would go an angle from the polar axis, I would go up pi over 3, and then I would go out a distance of 2. I have each ring being 0.5, so a distance of 2 would be right here. If I want to do the point Q, which is 2 comma negative pi over 3, well, we remember from earlier this year that we talked about a negative angle means that we're going to go clockwise instead of counterclockwise. So an angle of negative pi over 3, I'm going to start at the polar axis, and I'm going to go down pi over 3, so I end up on the same line as what's listed as 5 pi over 3, and then again, I'm going to go out a distance of 2 in my radius. So this would be point Q. So for the next point R, we're going to go an angle of pi over 3, so again we're going positive, which means it's going to go counterclockwise, so we're going to go up here, so the same place as where P is, but now it's saying a negative radius. So from the previous slide we said that a negative radius reflects you across the pole. So I'm going to go an angle of pi over 3, and then I'm going to reflect across the pole and go down 2 units in this direction. So point R would be right here. And then for our last one, we have a negative angle and a negative radius. So again, start with the angle. So a negative angle, negative pi over 3, I'm going to go clockwise pi over 3. And then I want to go a radius of negative 2. So that's going to reflect me across the pole, and I'm going to go up in this direction. So point S would be up here at this place. So one thing that we can notice is if we look at this point S, we got it from going negative pi over 3 and then negative 2, the point negative 2, negative pi over 3. You could have also labeled it a different way. I could have also started at the pole and gone a distance of 2 pi over 3 and then out a radius of positive 2. So unlike the xy plane, where every single point has a unique coordinate, in the polar plane, that's not true because of the way that angles, you can go clockwise, you can go counterclockwise, and then our radius, we can reflect across the pole, so on and so forth. So now we have a new point P, which is 1 comma 2 pi over 3. So first thing I want you to do is I want you to pause the video and graph that point on the polar plane, and then see if you can write 3 other coordinates that would give you the same point on the plane. So this is the point P, or I called it P sub 2 because it's our new P, 1 comma 2 pi over 3. So I went an angle of 2 pi over 3, and then I went out a radius of 1. So if you haven't already done so, pause the video and see if you can write this point using 3 other polar coordinates. So there's actually an infinite number because you can go around the circle as many times as you want, but I picked just the 4 basic ones. So the first one that I did was I said, well, I could have had a negative angle. So similar to what we did up here, I could have had a negative angle and then a positive radius. So what negative angle would get me to the same place? Well, that would be negative 4 pi over 3, and then I still want a radius of 1. So that would be the same location. Next, I thought of like this one that had a negative radius and a positive angle. So if I want a negative radius, that means I'm going to reflect across the pole to end up here, which means I want to have my angle be down here. So what angle gets me down here? Well, the angle would be 5 pi over 3, and then a negative radius would reflect me across the pole, and it'd get me to where I want to be. And then the last one, I did a negative radius and a negative angle. So again, to have a negative radius reflect across the pole and end up here, I want to start down here. And then what negative angle would get me down here? Well, that would be negative pi over 3. So when you're plotting points in the polar coordinate plane, we label them as r theta, but we always do the angle first and then the radius. A positive angle goes counterclockwise, a negative angle goes clockwise, a positive radius just goes out that distance from the pole, a negative radius reflects across the pole and goes backwards that distance. So just like in the Cartesian plane, we can have polar equations, so that would just be an equation that uses polar coordinates. And then a graph would be the set of all points r theta that satisfy that polar equation. So one polar equation would be r equals 3, or r equals some number. So I'm going to use a little r theta table here. So I'm going to have my independent variable right now be theta. So I'm going to pick some different angles. I just picked our quadrantal angles, 0, pi over 2, pi, 3 pi over 2, and 2 pi. Easy numbers. So then if my theta is 0, what is my radius? Well, my graph says, or my equation says that r equals 3. So then my r must be 3. If my angle is pi over 2, what's my radius? 3. Same thing all the way down because it just says that r is always 3. So now I'm going to plot this and see what graph this makes. So no matter what my angle was, my radius is always 3, and so that's the circle. I have a circle that has a radius of 3. Doesn't matter what the angle is, the radius is 3. So whenever you have r equals some number, that's just a circle that has the center at the origin. So the next equation that I'm going to look at is the equation theta equals pi over 4. So again, I'm going to make a little r theta table. This time I'm going to have r be my independent variable because I know theta. So if I have r be negative 3, what is my theta? Well, it tells me that theta is pi over 4, so theta must be pi over 4. If my radius is negative 2, what's my angle going to be? Well, it tells me my angle is going to be pi over 4, and so on and so forth all the way down. So no matter what my radius is, my angle is always pi over 4. So I'm going to plot this and see what this makes. So no matter what my radius was, my angle was pi over 4. So that ends up being a line that goes through the origin that makes an angle of pi over 4 with the polar axis. So whenever you have r equals a number, that's a circle with the center at the origin and a radius of whatever that number is. Whenever you have theta equals a number, that's a line that goes through the origin that makes that angle with the polar axis or the positive x-axis. So since we have two different forms now, we need to be able to convert between the two of them. So we need to be able to convert between rectangular coordinates x, y and polar coordinates r, theta. And we're going to use everything that we have that relates these things together, like our trig stuff. So sine of theta is y over r, so therefore y is the same thing as r sine theta. Cosine of theta is x over r, so therefore x is the same thing as r cosine theta. We can also use the equation of a circle or Pythagorean theorem, x squared plus y squared equals r squared. And then tangent of theta equals y over x. So all these things that we were using back in trig, we can now use them to help convert between polar and rectangular coordinates. So if we're given the polar coordinates 4, 3 pi over 4, we can use these things to convert them into rectangular coordinates. So go ahead and pause the video and see if you can do that. So I'm given r and theta, and I want to find x and y. So what I did is I used just the first two because I have that y is equal to r sine theta and x is equal to r cosine theta. So I just plugged in 4 for r and 3 pi over 4 for theta. And so for x, you get 4 cosine 3 pi over 4, which is 4 times negative root 2 over 2, or negative 2 root 2. And then for y, you get 4 sine 3 pi over 4, so 4 root 2 over 2, which is 2 root 2. So the coordinate in the xy plane that corresponds with the polar coordinate for 3 pi over 4 would be negative 2 root 2, comma 2 root 2. So now we want to go the other direction. So now we have xy coordinates, and we want to find the polar coordinates r theta. So go ahead and pause the video and do that. So the first thing I did was I found the radius first, just using that x squared plus y squared was r squared. So x was negative root 3, y was 1, and so I end up with negative root 3 quantity squared plus 1 squared is equal to r squared. So you end up with 3 plus 1, or 4, is equal to r squared, so therefore r is equal to 2. And then I used my radius that I just found and my y coordinate, and I set up that sine of theta is equal to y over r. So sine is equal to 1/2. Well, that's on my unit circle, so therefore theta has to be pi over 6. So my coordinate is 2 comma pi over 6. Now there's actually an infinite number of polar coordinates that would match with this rectangular coordinate, but I just went with the most basic one, my positive radius and my positive angle. We can also use these to help us convert equations between polar and rectangular. So for this first one, part A, we have the rectangular equation x is equal to 3. So use the information from the previous slide and convert this into a polar equation. So I just used the fact that x is equal to r cosine theta, and I just replaced the x in the original equation with r cosine theta. So the equivalent equation in polar form would be r cosine theta equals 3. For this next example, they give us the polar equation r equals 4 sine theta, and we want to convert this into a rectangular equation. So go ahead and pause the video and see if you can do this. There's a few different ways you can do this one. What I did is I started by converting sine of theta into y over r, so I now have r is equal to 4 times y over r, and then I multiplied both sides by r to get my radius out of the denominator, since r can't be 0 anyways, and so we end up with r squared is equal to 4y. But then, from Pythagorean theorem, we know that r squared is equal to x squared plus y squared. So x squared plus y squared is equal to 4y, and that is the equivalent equation in rectangular form. Next section, we'll get more in depth into polar equations and graphing polar equations, and we'll really look at what these look like. So for polar coordinates, again, you have r and theta. Theta is the angle it makes with the positive x-axis or the polar axis, and the radius is how far out it goes from the pole. A positive radius goes in the positive direction, a negative radius reflects across the pole and goes in the opposite direction.